So we can convert those numbers into scientific notation and engineering notation. We're going to start off today focusing on our scientific notation again. So we might have something like 2.3 times 10 to the 8th. If you recall, when we add or subtract numbers, there's a couple of things that we go by. The first thing that we have to be sure of is that we must have the same name. You know, when that was with just whole numbers with measurements, it had to be feet and feet or pounds and pounds. Fractions, it had to be common denominator. Even with whole numbers, you had to line up the columns so you could only combine digits with the same place value. In the scientific notation, what part of that implies a place value? Remember from our number line yesterday, is the 10 to the 8th was the place value. 10 to the 8th is actually the 100 millions. So in order to add numbers in scientific notation, they must have the same power of 10. So second, when we add numbers, we always combine the counts, but when we add or subtract, we keep the same name. So if I'm going to add numbers in scientific notation, let's say I've got my 2.3 times 10 to the 8th. My other number must also have the same power of 10, 10 to the 8th. So I might have 5.9 times 10 to the 8th. Now the parentheses there are not telling us to do anything first. They're just separating out, just like we do with negatives, we use parentheses to separate out that number from the rest. So we have the same name, we have the same power of 10, so we're going to combine the counts. 2.3 plus 5.9 is 8.2. And then we keep the same name, so 10 to the 8th. So we might have 7.4 times 10 to the negative 13th plus 2.1 times 10 to the negative 13th. Again, we have the same name. We're going to combine our counts. 7.4 plus 2.1 is 9.5, and we keep the same name, 10 to the negative 13th. Now, of course, it's not going to stay that simple. We're going to run into things like this. 8.3 times 10 to the 12th plus 5.8 times 10 to the 12th. They have the same name, so we can go ahead and combine them. We're going to combine the counts. 8.3 plus 5.8 is 14.1 times 10 to the 12th. What's wrong with that answer right now? Yeah, in scientific notation, we're only supposed to have one digit in front of the decimal point. Right now we have 2. So I have to move that decimal point over. Make it 1.41. But I have to adjust my power of 10. The decimal point went one position, one place value. So my power, remember, each place value is a power of 10. So I have to adjust my power of 10 by 1. How do I know whether they go larger or smaller? Well, did the number get bigger or smaller? I went from 14 to 1, so it got smaller. So the power has to get larger by 1. So 12 plus 1 is 13. So 1.41 times 10 to the 13th. We have to be a little careful with these. Take 7.8 times 10 to the negative 8 plus 6.4 times 10 to the negative 8. We do have the same power of 10, so we can add them. 7.8 plus 6.4 is 14.2 times 10 to the negative 8. Of course, we've got to move our decimal point again. Comes 1.42 times 10 to the Number got smaller, power gets larger. Negative 8 plus 1 is negative 7. A lot of people want to go to negative 9 for that. But bigger than negative 8 would be negative 7. What if we don't start out with the same power of 10? What if we have something like 6.43 times 10 to the 11th plus 9.3 times 10 to the 10th? Well, we're going to have to convert. Either this one's got to become 10 to the 10th or this one's going to have to become 10 to the 11th. When we are adding, we almost always go to the larger one. When we're adding, we do always go to the larger one. So this is going to stay 6.43 times 10 to the 11th. This is going to become times 10 to the 11th. Now it's the same thing we did up here, adjusting our decimal. The power got larger by 1, so the decimal point has to move 1 spot. Power got larger, the number has to get smaller by 1 spot. So this becomes 0.93. So 6.43 plus 0.93 is 7.36 times 10 to the 11th. So this, the power got larger, went from 10 to 11. So then I had to make the number smaller by 1 spot. If the power gets larger, number gets smaller. Power gets smaller, number gets larger. So then I added the numbers. 6.43 plus 0.93 is 7.36. And I keep the same name, 10 to the 11. I'm going to have you guys try one in your notes. (9.84) times 10 to the negative 13th plus 8.7 times 10 to the negative 14th. So what power are we going to convert both of those to? The negative 13 is the larger power. So this will stay 9.84 times 10 to the negative 13th. This is going to become 10 to the negative 13th. What's the number become? 0.87. So we add those. 9.84 plus 0.87 makes 10.71 times 10 to the negative 13th. That should be negative 13 there. Negative 13th. Of course, we still have to move the decimal point, so we can only have 1 digit in front of the decimal point. This becomes 10 to the negative 12. Very good. Any questions? Okay. Subtracting. Pretty much the same stuff. You must have the same name, same power of 10. These are both 10 to the negative 9. You're going to subtract. 9.4 minus 6.3 is 3.1. Subtract the counts. Keep the same name, 10 to the negative 9. Now again, it doesn't always end up that easy. We could have 4.72 times 10 to the 13th minus 3.94 times 10 to the 13th, which again, they do have the same name, so we don't have to adjust the powers of 10. But 4.72 minus 3.94 is 0.78 times 10 to the 13th. What's wrong with this answer? Now there's nothing in front of the decimal point. There's a 0. That don't count. So we have to move the decimal point this way to make this 7.8. Now this time the number got larger. It went from 0.78 to 7.8. So the number got larger. The power must get smaller. 13 minus 1 is 12. we can run into numbers that don't have the same power of 10, like 6.35 times 10 to the 9th minus 9.4 times 10 to the 8th. And just like before, we have to adjust. And we will go to the larger power. So 6.35 times 10 to the 9th. Let's stay there. This is going to become times 10 to the 9th. 9.4 is going to become 0.94. The power got larger, the number has to get smaller. Power got larger by 1, number is smaller by 1 place. So now we subtract 6.35 minus 0.94 is 5.41 times 10 to the 9th. So subtraction isn't so bad. If you can do addition, you can do subtraction. Let's look at multiplication. If you recall, when we multiply or divide 1, we do not need the same name. So for our scientific notation, that means we don't need the same power of 10. 2, we're always going to combine the counts. No matter what operation, we're going to combine the counts. But when we multiply or divide, we also combine the names. So let's take a look at what that looks like. So I might have 2.5 times 10 to the 7th times 1.8 times 10 to the 15th. They're not the same power of 10, but it doesn't matter. We're multiplying. When we multiply or divide, we do not need the same name. So we're just going to do 2.5 times 1.8, which is going to give us 4.5, correct? Times. Now when we multiply, we also combine the names. So 10 to the 7th times 10 to the 15th. Remember, when we're multiplying exponents with the same base, what do we do to the powers? Add them. 7 plus 15 is 22. That's 10 to the 22. Now, when we're multiplying, it's quite often that we'll run into this. 7.4 times 10 to the 9th times 3.5 times 10 to the 5th. We multiply 7.4 times 3.5, which gives us 25.9 times 10 to the 9th times 10 to the 5th. 14. Very good. Now, just like we had with addition, we've got to adjust that decimal point. We've got to move it over to make it 2.59. What happens to my power of 10 here? Larger or smaller? Larger. Yeah, number got smaller, power gets larger. So 10 to the 15th. It can become interesting when we start mixing in the negatives because we can have a mix of powers here. So we might have 5.2 times 10 to the 9th times 3.8 times 10 to the negative 14th. So 5.2 times 3.8, 19.76 times 10 to the, we have 9 and negative 14 is going to make negative 5. Very good. 9 plus negative 14 is negative 5. Now, of course, that's going to have to be adjusted. Got to move that over 1 to make 1.976 times 10 to the, number got smaller, power gets bigger. Negative 5 plus 1 is negative 4. I'll have you try one. Give that one a shot in your notes. One you tried 6.5 times 4.8. Oops, I get my decimal in there. Get back there. Gives us 31.2 times 10 to the negative 9th times 10 to the 18th is 9. And of course we have to adjust that to 3.12 times 10 to the 10th. Very good. Any questions on those? Okay. So now we got to do division. Division is the same way. We combine counts, but we also have to combine the names. So we might have 4.2 times 10 to the 7th divided by 1.4 times 10 to the 18th. So we'll combine the counts. 4.2 divided by 1.4 is just 3. Then we combine the names. Now remember, when we divide exponents with the same base, what do we do to the powers? When we're dividing, we're going to subtract the powers. So 10 to the 7th divided by 10 to the 18th is going to be 10. 7 minus 18 is a negative 11. So it's 3 times 10 to the negative 11th. So we might have 1.728 times 10 to the negative 5th divided by 1.2 times 10 to the negative 14th. 1.728 divided by 1.2 is 1.44. 10 to the negative 5th divided by 10 to the negative 14th. Negative 5 minus a negative 14 is positive 9. Very good. Now, just like we've had with addition, subtraction, and multiplication, we can have answers where we have to adjust it. We might have 5.76 times 10 to the 8th divided by 4.8 times 10 to the negative 11th. 5.76 divided by 4.8 is 1.2 times 10 to the 19th. Very good. 8 minus a negative 11 is 19. If I have 4.8 times 10 to the 4th divided by 5.76 times 10 to the negative 9th, 4.8 divided by 5.76 is 0.833333, right? Times, we're going to just round it to 0.833, times 10 to the 13th. Good. Can't leave it like that, though. What are we going to have to do? Move it over one spot. 8.3 times 10 to the 13th. 10 to the 12th, thank you. Number got bigger, power does have to get smaller, so it goes from 13 to the 12th. Thanks. Okay, so the last thing to do with scientific notation is to look at powers. So we have 1.2 times 10 to the 7th squared. So we've got to do 1.2 squared. Just like we do anything else, we've got to square the count. So 1.2 squared is 1.44. Then we've got to square the names. 10 to the 7th squared. What do we do to the power when we take a power of a power? If I just 10 to the 7th squared, it would be 7 times 2, right? So the 14th. Very good. So I might have 3.
1.2 times 2?
I had 1.2 squared, so it's 1.2 times 1.2 times itself. So let's say I have 3.8 times 10 to the negative fifth to the fourth power. So I have to do 3.8 to the fourth power. (208.5136). Now the power of 10 is 10 to the, I have to do negative 5 times 4 is negative 20. Now I have to adjust the answer here because there's 3 digits in front of the decimal point. I have to go 2 spots. 2.085, always are 2.085. And yes, we had to move it 2 spots. So now the power of 10 has to be adjusted by 2. Number got smaller, the power gets larger. So negative 20 plus 2 is a negative 18. Any questions? Engineering notation. When we go to do operations with engineering notation, we looked at this briefly last class. Remember we said engineering notation is dealing with those metric prefixes. Like if we have a volt or an amp or an ohm or whatever, that main unit is 1 or 10 to the 0. Then if we have milli, that's 10 to the negative 3. Micro is 10 to the negative 6, or 1 millionth. Going the other way, kilo is 10 to the third, or 1,000. Going the other way, keep going, mega is a million, or 10 to the 6th. So look at voltage. Volts equal to current times resistance. So if I am told that my current is 12 microamps, that little mu, it's called mu, it looks like a U with a long tail, that's micro. And my resistance is 2.5 kilo ohms. That little upside down horseshoe is the ohms. So I'm going to be multiplying here is my 12 microamps times 2.5 kilo ohms. This can be done by using engineering notation in place of the metric prefixes. These are our engineering notation here. So instead of 12 microamps, that's 12 times 10 to the negative 6 amps. Multiplied by 2.5 kilo ohms is going to be 2.5 times 10 to the positive 3 ohms. So now we do 12 times 2.5 is 30. 10 to the negative 6 times 10 to the third is 10 to the negative 3. Negative 6 plus 3. And now this part you guys wouldn't know, but I wouldn't expect you to know at least. Amps times ohms is a volt. So this comes out to be 30, 10 to the negative 3 is millivolts. Does that make sense?
Nothing to do with that.
Very little.
Okay.
There might be 1 or 2 on a quiz. Another electrical formula is power is equal to voltage squared divided by resistance. So if your voltage is 50 kilovolts and your resistance is 30 kilo ohms, this is going to become 50 kilovolts squared over 30 kilo ohms. So this is going to be 50 kilos times 10 to the third volts squared over 30 times 10 to the third ohms. So now up top, we're going to have to square this. 50 squared is 2,500. 10 to the third squared is 10 to the sixth. Volt squared is volt squared. We still got to do that. Now, technically, this is improper right now because there's more than 3 digits. Scientific or engineering notation should never have more than 3 digits in front of the decimal point. But we're still going to have to do some calculations with this. We still have to divide by the 30 times 10 to the third. So let's do that first before we adjust it. So 2,500 divided by 30 is 833. Is that correct? No, 83.3. 83.3 times 10 to the 6th divided by 10 to the third is 10 to the third. Volt squared divided by an ohm, again, I wouldn't expect you to know this. That's a watt. And so that is 83.3 times 10 to the third is kilowatts. On a test or quiz, I would never expect you to know that a volt squared divided by an ohm is a watt, or that an amp times a volt or an amp times an ohm is a volt. But I would expect you to know how to work with the powers and the metric prefixes. So homework for you. Page 208 to 210. Exercise 612C. 1 through 33, the odds. And so do the odds. And on page 213, exercise 613C. Again, do the odds. An amp times an ohm is a volt. An amp times a volt is a watt. A volt divided by an amp is an ohm. There's a whole list of them. A volt squared divided by an ohm is a watt. Those are the ones you'll see the most of. Again, I wouldn't expect you to memorize those. This for an electricity class, I'd make you have those memorized. Everybody have those down?
No.
Okay, I'll leave them there for a minute.